Chapter 9 Fakie. So for BH3, there's only going to be 3 bonds on the boron. Boron gets bullied is my phrase for it. Boron is one of the exceptions to the octet rule. It does not get an octet. It is not strong enough to demand an octet. It can't handle 4 bonds. It's going to get 3 bonds. So that means that there are 3 bonds distributed as far apart as they can get in 3-dimensional space. That would be trigonal planar at 120 degrees. And they do think you know the simple shapes and the simple angles. What's the hybridization? This has 3 sigma bonds, no pi bonds, 3 sigma bonds, no pi bonds, and no unshared pairs. That means it needs 3 hybrid orbitals. That's 1 from the s and 2 from the p subshells. Sigma bonds are the single bonds and the first of any double or triples. I don't have any double or triples, therefore I don't have any pi bonds. The pi bonds are the second or third of any double or triple bonds. This is symmetrical, so it is nonpolar. It can't have both a plus and a minus side if it's essentially the same in all directions, which means it has London dispersion forces only. The formal charge would be 3 valence minus 3 bonds and 0 unshared pairs. So that's formal charge 0. This is 1 valence minus 1 bond and no unshared pairs. There we go. And that's 0 formal charge. On O2, now I just happen to know that this is a double bond, but you basically have to have a double bond or you just don't make the octet rule work. And oxygen will want an octet. I can't even think of an exception to the octet rule for oxygen. Sometimes its formal charge is not 0 or its oxidation number is not 0, but it will get an octet. And how many valence do we get? Well, we get 6 and 6 is 12, 2, 4, 6, 8, 10, 12. So you need a double bond in here to make the octet rule work. With any 2 atoms only, you can only get linear at 180 degrees. It needs, so for the hybridization, I have 1 sigma bond, the first one of the double bond, and I have 1 pi bond, the second one, whichever one that is, of the double bond. And then for the hybridization, I use the sigma bond, that's why I was pointing that out, and the 2 unshared pairs for the hybridization. So I have 3 pairs that need hybridization. The sigma, the first one here, and the 2 unshared pairs. So I need to borrow 3 orbitals, 1 s and 2 p's for the hybridization. This is obviously symmetrical. That means it's nonpolar, and that means it has London dispersion forces only. The formal charge had darn well better be 0 on these because they're identical and the overall charge is 0, but we will prove it. 6 valence minus any 2 atoms can only be linear at 180 degrees. What's the bonds that I have? The first one of any double bond is a sigma. The second one is pi. I don't know why sigma and pi, but that's what we're using. That means I have 3 pairs of electrons that need hybridization. The first bond of the 2, the sigma bond, and the 2 unshared pairs. So I need to borrow 3 orbitals. That is 1 from the s and 2 from the p subshells. And remember, that does not mean electrons. That is number of orbitals borrowed. It's symmetrical, obviously, so it is nonpolar with London dispersion forces only. The formal charge will be 6 valence minus 4 unshared electrons, not the pairs, the electrons, not the pairs, the total unshared electrons, and the 2 bonds, or 1 from each bond. And that gives me a formal charge of 0. Water is kind of the absolute classic. So let's review that because, you know, this kind of thing comes up, plus it's a good example. So we get the H's attached with obviously covalent bonds, and that means the oxygens. We get the H's attached with covalent bonds, and that means the oxygen has 2 unshared pairs. That is bent, and I had to look it up myself, but it's 104.5 degrees, and they do think you kind of know that, and they, in my experience, will say something like, which is the closest bond angle or something, and then they say, your choice is like 105 degrees or something. In fact, then also I've seen when it was free response that they accept anything from, I think, like 104 to 107 or something like that. Anyway, there's a range. How many bonds do I have of what type? I have 2 single bonds, that's 2 sigmas, and no doubles or triples, so that's no pi's. The hybridization then is the 2 sigma bonds and the 2 unshared pairs. That's 4 orbitals needing hybridization, so I need 1 s and 3 p's for the hybridization. This is hydrogen bonding is the strongest bonding because it's not ionic, so it's not that. Hydrogen bonding is the next strongest bonding. It's when H is on oxygen or nitrogen or fluorine, and then it becomes kind of extrapolar. This bonding pair here gets extra stolen, even compared to most times, and this becomes extra plus and this becomes extra minus, which means it's even more attractive to the next water molecule next to it. So the polarity arrow goes toward the more electronegative atom. This is obviously much closer to fluorine than hydrogen is. So we go arrow toward the negative side. Traditionally, we put a little plus on the tail of the arrow to indicate the plus side. Remember, you must have what's called a dipole moment to have polarity. Can I find the plus and minus side? Yes, there's the minus side, there's the plus side. Now, I realize going back, I even confused myself. So notice I have changed something here. I have rewritten this as a sigma and a sigma. I realized I was writing lowercase deltas previously, so I have changed this. Here is a lowercase delta, and remember, this is the relative, the lowercase version of, that's the triangle, that's the capital letter in Greek, and this has come to mean change in. So if that is change in, I suppose this is a little bit of change in. And I don't know if that's supposed to be a joke or whatever, but this is what we're using. So there has been a partial change in the charges of this to where this is a little bit minus and this is a little bit plus. Except my point with water is that it's extra compared to most. So you can see it's a little bit in that it's not fully ionic. This is not fully negative. This is not fully positive. But compared to most things, it's a lot negative and a lot positive. And that's why it's hydrogen bonding. That's why it's a special case that we talk about when H has its bonds stolen more than usual, much more than usual, by something like oxygen or nitrogen or fluorine. So we draw the arrow to the negative side and we put a plus on the positive side. And that's my polarity indication. The formal charge would be 6 valence minus 4 unshared electrons, and the 2 bonds is 0. 1 valence minus no unshared pairs, and the 1 bond is 0. Let's prove which structure is preferred, because it is very tempting to say this one. In fact, I taught this for years. I realize no one's career will be ruined by this, but it is a very interesting point that this is not the correct version. This is definitely the preferred version because of the formal charges, and let's prove it. And I realized that I think I've switched it up and I've started naming the bonds first, but it doesn't matter mathematically if you count the bonds first or the unshared pairs first, as long as you subtract out the total. So I have 6 valence minus 6 bonds and no unshared electrons is 0. I have 6 valence minus 2 bonds and 4 unshared electrons is 0. That's for these. 6 valence minus 1 bond and 6 unshared electrons is -1. That happens twice, of course. So yes, it does match the overall charge. It's 2 minus. Sulfur is 6 valence minus 4 bonds and no unshared electrons is +2. Oxygen is 6 valence minus 1 bond and 6 unshared electrons is -1, but this happens 4 times. So this is essentially -4 total. And yes, the charges match, that this is -2 total now, and it is 2 minus, but this is much preferred. This has more 0 charges. That's the first thing I notice. It has 0 in the center atom. Well, that is also preferred, and has the negative charge on the more electronegative species. Or in a more general way, adding this up is a lot less complicated than adding that up, and that's the version that nature prefers.